In this video, we're going to talk about determining RNS configurations for Fischer projections, okay? And we say that a atom is chiral if we have four different chiral centers, four different atoms, things bonded to it. So to me, it looks as if this carbon is chiral and this carbon is chiral. So the number of stereoisomers we could get is 2 to the n, where n is the number of chiral centers. So therefore, 2 to the n, 2 squared is 4. So we get 4 different stereoisomers for this compound. So my question is what are the configurations around it? Is it R or S? Okay, well, that's nice to know. So again, I'm going to draw my chiral center of interest to the side. Okay. And I'm going to look at what's bonded to it. So I have a hydrogen. It's bonded to a hydrogen. It's bonded to a bromine. And it has a carbon on top. And it's bonded to a carbon on the bottom, which is this carbon here. Okay. So to me, it looks as if the bromine will get product group number 1. Or hydrogen will get product group number 4. Now we're gonna list whatever the carbon is bonded to in decrease in atomic mass. In this case, it has 3 hydrogens, so it has 3 hydrogens. Okay, and this carbon is bonded to a bromine and a hydrogen. So we'll list them in decreased atomic mass to whatever they're bonded to. Okay, so to me it looks as if the bromine will win out. So I go 1 out, I get a bromine, I go 1 out, I get a hydrogen. So therefore this has to be product group number 2. So therefore this has to be product group number 3. So we go 1 to 2 to 3. Okay, so notice we're going S, but again, because of Fischer projections, we're going to take the opposite and say it's going R. Now, this is a disclaimer, guys. There are several ways of going about this thing here. So your professor might teach you a different way. The good point is that these are basically multiple choice, kind of 50-50%. Is it R and S? So we don't care about how you get there. What we care about is, did you get the right answer? Okay. So this is how I'm going to do my Fischer projections. Okay. So if I'm looking at the second one, I'm going to draw my chiral center of interest. So I have my bromine, and it's bonded to a hydrogen that's bonded to a carbon, and it's bonded to a carbon. Okay. Now it looks as if to me that the bromine will get product group number 1. It's heavier than any one of these atoms around it. Okay. Now the question is, which one of these went out? Okay. Well, we know hydrogen gets product group number 4. Okay. But the question is, which one of these went out? Okay, well, to me, it looks as if this carbon, in terms of decrease in atomic mass, is bonded to a bromine, a hydrogen. This carbon, in terms of decrease in atomic mass, is bonded to 3 hydrogens. Okay, so definitely going 1 out ahead of bromine, going 1 out ahead of hydrogen. Bromine is heavier than the hydrogen, so therefore this gets product group number 2. This gets 3, so it goes to 1 to 2 to 3. So it's going S again. Okay, it's going S again. But we're going to take the opposite and say this is R. Now, how could we draw the enantiomer of this compound? Well, remember we said that enantiomers, okay? Yeah, so I totally screwed this up. Yeah, let's draw it. So how do we get the enantiomer of this compound? I didn't want to do it this way. Okay, so draw the same compound twice, but okay, that's fine. So how do we take the enantiomer of this compound? Remember we said that enantiomers we have alternating chiral centers in terms of Fischer projections. Okay, so to get the enantiomer, all I'm going to do is switch my horizontal lines. So therefore my bromine will come over here. My hydrogen will therefore come over here. And then my bromine will come over here. My hydrogen will come over here. And so these are enantiomers. Okay. So to get the enantiomer, you gotta switch your chiral centers, both. Okay, we gotta switch both. Now, how could we get the diastereomer of this molecule here? How could we get the diastereomers of this molecule here? So I'm gonna redraw the original molecule. Okay, and how could we get the diastereomer of this molecule here? Well, remember we classified diastereomers as having more than one chiral center with one staying the same. So therefore I could look at this as a CH3. I'm going to keep one of my chiral centers the same, and I'm going to switch one. Okay, so these are what we call diastereomers. Now, in fact, this is actually a meso compound, and the reason why it is because we could find some plane of symmetry and draw a horizontal line through it, and you could see that we get two equal halves of the molecule. Okay, so looking through this plane of symmetry, so this is actually a meso compound. So that's how we find meso compounds in terms of Fischer projection. That's a meso compound, okay? But in terms of what these two molecules are, these are diastereomers. And notice the difference. Enantiomers, we're stretching both chiral centers. Diastereomer, we stick with one, staying the same, and the other changing. Okay, now let's look at another one. What if I wanted to, what if I gave you this molecule here, okay? And we wanted to determine whether it's R or S configured. Okay, there's a chiral center R and S configured. Well, to me, it looks as if my chiral center is there. Okay, well, that's nice to know. And then we're going to draw a chiral center of interest. Okay, so this is bonded to an oxygen, that's bonded to a carbon, that's bonded to a carbon, that's bonded to a hydrogen. Well, it looks to me as if the oxygen is heavier, so we'll get priority group number 1. Now, the question is, which one of these will win out? Okay, and we have a double bond. Remember, we talk about ghost atoms, okay? Ghost atoms. And what does that mean? We're going to draw, anytime we see a carbon that's double bonded to an oxygen, we have to make a decision. We're going to draw it as a carbon that's bonded to two separate oxygen, okay? And this is only for optical activity purposes and determine the RNS, not trivial, okay? So if I place my, whatever the carbon is bonded to on, in decreasing atomic mass, we have the carbon that's bonded to an oxygen, and a hydrogen, okay? Now this one is bonded to an oxygen, a hydrogen, and a hydrogen. So it's pretty evident to me that going one out will be equal, but if we go the next one out at an oxygen and hit a hydrogen, so therefore this has to be party group number 2, this has to be 3. Well, we don't care about the hydrogen, but just know it's 4. And we go from this way to this way, so we're going R again. Well, I'm sorry, but we're going S. Okay, we're going S, but we're going to take the opposite and say this is R configured. Now, I want to take a look at something special here. Okay, so what about this one? Okay, what about this one? What are the chiral centers? Well, to me, I see that I have 4 different chiral centers all lining down here. So, okay, we have 4 different chiral centers. And I want to determine the R or S configuration for it, for each, okay? So again, remember, we're going to draw our chiral centers apart. Okay, so for the first chiral center, it's bonded to an oxygen, it's bonded to a hydrogen, okay? And it's bonded to a carbon. It's bonded also to this carbon here. So it's bonded to this carbon, this hydrogen, this oxygen. Okay, so it looks as if to me oxygen will always win out with carbons. Okay, hydrogen gets part of group number 4. Okay. Okay, oxygen gets part of group number 4, and then remember we draw ghost atoms. So therefore, in terms of decrease in atomic mass and priority, we're going to view this as an oxygen, and a hydrogen. For the other one, it's bonded to an oxygen and a hydrogen. So it's bonded to an oxygen, hydrogen, decrease in atomic mass. It was pretty evident to me that if I go one out, I hit an oxygen. If I go one more out, I hit an oxygen and hydrogen. So therefore, an oxygen is heavier than a hydrogen. So this gets part of group number 2. This gets 3. My stuff is going S, but again, we're going to take the opposite. They say it's R. Okay, now what about this one? If I draw my chiral center of interest, it's bonded to a hydrogen, it's bonded to an O, it's bonded to a carbon, it's bonded to a carbon. Okay, now I want you to look very closely. If I'm talking about this chiral center of interest, notice that if I go one out, I hit a carbon and I hit a carbon, which is exactly what I have here. But notice, these are they're equal. So notice I have an oxygen, a hydrogen, oxygen, hydrogen. So in fact, these two will not give me any conclusions as to what the configuration is about the carbon. So therefore, I got to go one more out. And if I go one more out, I hit this one and I hit this one. Okay, so let me put an arrow. I hit this one and I hit this one. So these are now the new carbons, the new carbons, I guess the thing that is bonded to that we're going to use and say, okay, well, this is where we're going to make our conclusion from. So it looks to me as if an oxygen will always get group number 1, but this carbon now, we're going to pretend it's bonded to an oxygen, a hydrogen, because we're now the aldehyde group. And this one, we're at an oxygen, hydrogen, and hydrogen. Okay. Now it looks to me as if I go one out, I hit both, so these are the same. But if I go one more out, you could definitely see that this one's out. Okay. You could definitely see that this one's out. And so therefore, this is part of group number 2. This is 3. So therefore, it's going R. Okay, it's going R, but in fact, we're going to take the opposite and say this is S. Now, what about the third Chiral center for interest, the third one? So I have a carbon that's bonded to an oxygen, and it's bonded to a hydrogen, it's bonded to a carbon, it's bonded to a carbon. Well, it looks to me like an oxygen will get priority group number 1. Okay, and now we're so we're looking at this Chiral center, okay, and now we're gonna assign priority groups, okay. So I want you guys to take a look here. If I'm looking at this chiral carbon, if I go one out, I hit an OHH. If I go one out, I hit an OHH. So these two will not give me any conclusion as to what the chiral center configuration may be. Now I got to go one more out. So if I go one more out, I hit an OHH and I hit an OHHH. So therefore, if I'm looking at this, this is an O, H, H, H. Okay. And now we're here. This is an O, H, H. Okay. Now, which one wins out? Well, we got to go in order. So if I go one out, one more out, they're both tied. If we go a hydrogen, we hit a hydrogen. If we go one more hydrogen, we hit a hydrogen. Okay. Well, if I go one more out, what do I hit here? If I go one more out from here, I hit a hydrogen. But if I go one more out, well, this now is used up. So we got to go one more out. And the next atom we hit from this is the carbon. So the next atom from this is a carbon. So therefore, a carbon is way much more heavier than a hydrogen. So this gets priority group number 2. This gets 3. Okay, so it goes from 1 to 2 to 3. So it's going S. Okay, it's going S, but in fact, this is R configured. Okay, now what about the last one? Okay, what about the last one? We have a carbon that's bonded to an oxygen, and it's bonded to a hydrogen. Okay, it's bonded to a carbon, and it's bonded to a carbon. Okay, now it looks to me as if this carbon will get priority group number 1. So it's this oxygen, because it's heavier than both carbons. We know hydrogen gets priority group number 4. Now, my question to you is, which one is heavier? So in terms of decrease in atomic mass, we have an oxygen, hydrogen, hydrogen. And for this one, we have an oxygen, hydrogen, hydrogen, hydrogen. Okay. Okay, 3 hydrogens come from here, and the oxygen and 2 hydrogens. So up until this point, if I go one out, one out, one out, one out, one out, we're all equal. Okay. Well, what's the next one do we hit here? We used up this, so we got to go to the next atom we're going to hit. And in fact, it's going to be a carbon. Okay. So you can see that we use these up and we got to go on. Okay. So the next atom we hit is carbon. The next atom we hit here is a hydrogen. So carbon is heavier than hydrogen. So it gets priority group number 2. So therefore, this has to be 3. And the arrow goes from 1 to 2 to 3, which is S. So in fact, this is R. Okay. Now this molecule is D plus glucose. Okay. So this molecule is glucose. Okay. So glucose is what we've been playing with, and we define glucose as being R, S, R, R. Okay. That's how we define glucose as being R, S, R, R. Now, I want to talk about an important concept here. And again, we're going to talk about the idea of enantiomer. So how could we get the diastereomer of glucose? Okay, so let me redraw the molecule. Okay, so let me redraw the molecule. Okay, so this is what glucose is. So we call this D plus glucose. And the reason why there's a plus is because you could guess it rotates plain polarized light to the right.